Swayam Prabha. Digital India. Educated India.
Fine. Now come to your question, right? What is memory aliasing? We have already seen this memory aliasing, right? Now I have load R4 plus 50 comma R2, store R3 to R5 plus 70. That means this is write R3 into address R5 plus 70, read R2 from address R4 plus 50, right. Now if R5 plus 70 is equal to R4 plus 50, then we have a raw hazard, because this is reading from R4 plus 50, read from address R4 plus 50 into R2. Okay. This is reading from address R4 plus 50, while this is writing into address R5 plus 70. So this becomes, this is a read on the memory, this is a write on the memory, so this becomes read after write. Okay. This becomes read after write. So how do we handle this? For if I treat every memory location, as a register, then this is done, right? Because when I am doing the load, I know that this, I know the address. So if I will go and tell for this address, for every address if I have a location, then what will happen? For this address, the latest value is not there in the address, but it is currently computed by an execution unit. So whatever I have done for register, I can do it for this. If for every address, if I am going to have a indicator, like register status indicator, I will have memory address status indicator. So if I am writing into 5, then I will have an indicator for 5. 5 will say that this is the latest value of 5 is not in the memory 5, but it is currently computed by some unit 8. So when I am reading from 5, I will not get it from 5, but I will wait for this 8. I am happy because it will come very fast rather than going into the memory. You are getting this? Are you able to follow? Yes or no? Right? But I can't have, if I have today 32 GB memory I have, can I have 32 GB register status indicator, or is it necessary? It is not necessary, right. So what we, the way we solve is, we use the concept of what we call as CAM, content addressable memory. Okay. Content addressable memory. So I will talk about content addressable memory in the okay. Do you all follow this? Now I will go to content addressable memory. So I will, what is content address? What is normal memory? Normal memory, I give an address, right, and I get the content of that address. So let us say this is 1, 5, 7, 8, 10, 11, the address is 0, 1, 2, 3, 4, 5. So, when I give 0, I get 1 because this is 1. When I give say 5, I get 11. So, I give the address and get the answer. So, this is a normal memory. But a content addressable memory, which we call it as CAM, say it has some 3 locations. Let me say I am storing some 15, 25, 72. I go and ask a query, array is 15 there? Then it will say yes. And it will also give you some data associated with 16. Let me call it D1, D2, D3. It will also give you the data. If I go and ask query is 15, it say yes. Suppose I go and ask query is 23, it will say no. Suppose I ask query is 72, it will say yes, and it will also give me the data associated with it, which is D3. So, I am addressing the content, not the location. I am addressing whether this content belongs there. So, there is a difference between how I am addressing the top memory and how I normal memory and how I am addressing the content addressable memory. So, when in the content addressable memory, basically I will send a query, and if that query element belongs to anywhere in the content addressable memory, this fellow will say yes, and it will also send some data associated with it. If the query element is not there in the content addressable memory, then it will say no. Okay. So, this is the so please note that the content addressable memory will consume several times more data, more area and power, and that is why I can't have large content addressable memories, right. It will consume lot of area and power in comparison to the normal memory. That is why I can't realize large content addressable memories in the system. Okay. Now, basically it is like I have a set and I am asking for a membership query for that set. Set 2, 3, 4, 5, is 2 a member, is 4 a member, right. This is a membership query for the set. Understood? Clear? Yes? No? Okay. Now, how will I use content addressable memory for this? How do I use a content addressable memory for this? I use a content addressable memory for this. Suppose last time we had no store R3 to R4 plus 75, load R7 plus 80 into R10, something like that. Okay. So, the moment I am getting in the content addressable memory, moment I am getting R4, let R4 be 1000. In the content addressable memory, I will put 1075. And suppose this instruction is allotted to execution unit say 5, I will put E5 also here. So, in the content addressable memory, I will store 1075 and I will put E5. This essentially says that if somebody wants to read from 1075, that 1075 is not there in 1075 in the memory, it is currently being computed, the latest value is currently being computed in the execution unit E5. Are you able to follow? Now, when this fellow wants to read, he wants to read from memory, this fellow is writing into memory, correct. I will calculate R7 plus 80. Now, suppose this is 995, R7 is 995 plus 80, then suppose R7 is also say some 500. So, the answer would be 580. I will go, the moment I get 580, I will go to this content addressable memory and ask, hey Baba, 580 is there. That fellow will say no. That means there is no problem for me, right. But our luck, suppose R7 is 995, 995 plus 80 is 1075. Before loading, I will go and ask, hey, it is there. This fellow will say, yeah, it is here. So, immediately what you will do? You will go to the reservation station and wait for this execution unit 5. and that answer you take and load it into R10. Actually you will be happy because you need not go all the way to cache, then to memory, and so many things we are going to talk of. Are you able to follow this? So your read after write hazard will get handled. So essentially what is going to happen, if I am going to have a content addressable memory like this, then what will happen, I can handle memory aliasing problem also, like the way I am going to handle the register issue. All the var, waf and raw can be handled so like this, correct, and the operand forwarding also happens, your renaming can also happen. Renaming happens with the unit number. Now before coming to your question, what should be the size of this content addressable memory? At the most how many loads can happen, it is equal to the number of units. So there will be at most 4 load store units. So the content addressable memory I just need 4 locations, right. So what was my crib about content addressable memory in contrast to normal memory? The content addressable memory takes lot of area and time, correct. Content addressable memory takes lot of area and power. Now if I am going to have 1 giga content addressable memory, that is all, the chip will be content addressable memory, not CPU, okay. You will spend more time on that. It will consume 1 megawatt substation of nuclear power for doing this, okay, right, that will be too costly. Now but I do not need that much, I just need 4, and by this I can handle the real thorn in the flesh. What is it? Memory aliasing problem. Dynamically I can handle. Understood? Clear? Yes. Writing to the saved location, that is okay. So the last location I have to store. So suppose this is you mean say store R3, R4, 75, again store R6, R8 plus 60, while R8 turns out to be 1000, sorry, correct? There is a store R3, R4 plus 75 followed by store R6, R8 plus 60, where R8 is 1015. Then what you do, you just make, suppose this store is currently allocated to execution unit 8, okay. So you make this E8, that is all. We handle not 2 fellows writing into the R1 also. So all the subsequent instructions beyond that should do this. But when you are writing back, the reorder buffer will see that it is committing the latest value, okay. So what we have done, we now have a piece of hardware which can handle raw, write and this dynamically. Your computer as such, again I repeat, your computer can be as idiot as me, the hardware is as intelligent as you, okay, you can do that, fine. So the point is, it can be, we are doing this entirely in the hardware, it is done dynamically, that is why we call it as dynamic instruction scheduling, because dynamically I go and schedule, I go and say dynamically I have gone and said, so this instruction will go to 1 and start executing, this instruction will go to this instruction will go to 2 and wait, 3, and all these things I have done. Who has done this? Hardware has done it, and it has scheduled every instruction to this unit and say execute or wait. So this is basically scheduling, and this is done when the program is in execution. So that is why we call it as dynamic instruction scheduling. Got this? Okay, fine. So the next we will go into the okay. So these small things. See that operand forwarding and register renaming is done automatically here, and then when the execution unit 6 on completion will make R1 entry to 0 if still it is 6, because there may be other instructions which have changed it, and similarly unit 4 will make R7 entry as 0, right, and then we have seen the memory aliasing problem.